Hello and welcome to another exciting tutorial. Today we are diving into the world of algorithms and coding by tackling one of the intriguing problems from LeetCode, a Roman to integer. Now you might be wondering why we are exploring Roman numerals in the realm of programming. Well, understanding and solving this problem not only sharpens your coding skills, but also provides a fascinating glimpse into the history of numerical systems. It's a great exercise in algorithmic thinking. And from the simplicity of I to the grandeur of M, these symbols have a rich history dating back to ancient Rome and are still encountered in various aspects of modern life. So if you are ready to embark on this coding journey and learn how to decipher Roman numerals like a pro, let's get started with Roman to integer. But before we start, if you haven't already, be sure to hit that subscribe button and give this video a thumbs up if you find this tutorial helpful. And don't forget to ring the notification bell so you won't miss any of the future coding adventures. Before we dive into the nitty-gritty of the code, let's take a moment to explore the intuition behind our solution to the Roman to integer problem. Understanding the core ideas will make it much easier to grasp the code that follows. These symbols such as I, V, X, L, C, D, and M were used by the ancient Romans for counting and record keeping, and each symbol represents a specific value. And the clever arrangement of these symbols led to a versatile numeric system. Now, when it comes to converting Roman numerals into integers, we need to keep a few fundamental rules in mind. Roman numerals are usually written from largest to smallest, from left to right. However, there are special cases where subtraction is used, like IV for 4 and IX for 9. And to handle these subtraction cases, we need to compare the values of adjacent characters. If the current character's value is less than the next character's value, we subtract it. Our solution leverages this insight. We iterate through the Roman numeral string, character by character, while comparing values. If the current character's value is greater than or equal to the next character's value, we add it to our running total. This covers cases where numerals are simply added together. But here's where the real magic happens. When the current character's value is less than the next character's value, we subtract it. Why? Because Roman numerals are inherently designed this way. When a smaller numeral appears before a large one, you subtract the smaller one to get the correct value. To make this process efficient and elegant, we use a dictionary that maps each Roman numeral character to its integer value. This dictionary acts as our guide, making it quick and easy to look up values. And we also keep track of the previous character's value because in certain cases like IV, we need to subtract twice the previous value to account for the subtraction. So the intuition behind our solution is all about navigating the intricacies of Roman numerals using these rules and cleverly calculating the final integer value step by step. And let's delve into another critical aspect of our code. It's time and space complexities. Understanding these complexities will help us appreciate just how efficient our solution is. This metric tells us how the runtime of our code scales with the size of the input, the time complexity. So in our case, the input is the Roman numeral string, which we will call S. Our solution boasts a fantastic linear time complexity of O of n, big O of n. That means the time it takes to execute our code grows linearly with the length of the input stream S. Why is that? Well, we have a single loop that iterates through the stream exactly once, examining each character. Regardless of how long the Roman numeral is, we only perform a constant amount of work for each character. This linear relationship between input size and runtime makes our code highly efficient. And now let's shift our focus to space complexity. This metric tells us how the memory usage of our code scales with input size. Our solution excels here as well. With the constant space complexity of big O of 1, this means that the amount of memory our code uses remains essentially the same, regardless of the size of the Roman numeral string S. Why is that the case? We use the fixed size dictionary to map Roman numeral characters to integer values. The size of this dictionary doesn't depend on the input size. It's constant. Additionally, we use only a small number of variables, such as number, which also consume a constant amount of memory. This efficient use of memory ensures that our code can handle even the longest Roman numerals without excessive memory usage. In summary, our Roman to integer solution is not only elegant in its approach, but also highly efficient in terms of time and space complexities. It performs the conversion in a linear fashion, and its memory usage remains constant, making it a fantastic choice for handling Roman numerals of any length. And there you have it, folks. We have successfully journeyed through the intricacies of the Roman to integer problem. And I hope you found this tutorial not only enlightening, but also fun. By now, you should have a solid grasp of how to approach and solve this problem efficiently using the approach we discussed. Remember, problem solving is not just about writing code, it's about breaking down complex challenges into manageable steps. And we have certainly done that today. I encourage you to explore more LeetCode problems, tackle them using your newfound skills, and continue your coding journey. Remember, every problem you solve is a step toward becoming a better programmer. If you enjoyed this tutorial and found it helpful, please don't forget to like, share, and subscribe to my channel. Your support means the world to me. Thank you for joining me on this coding adventure today. I look forward to seeing you in our future tutorials. Until next time, happy coding and keep those algorithms sharp. Goodbye.